There's some vocabulary terms you would definitely want to know before learning about relative dating, the principle of superposition, all sorts of things like that. Let's go ahead and move on from here. We're going to start with what is the principle of superposition. So the principle of superposition states that the oldest rocks will be found at the bottom, and by going off of that, the youngest rocks should be found on the top of any stratigraphic sequence. However, that only holds true if the rocks are undisturbed, which we'll go on a little bit later and talk about that. So here we have a layer of rocks, well, quite a few layers of rocks, and going off the principle of superposition, this layer should be the oldest, younger, 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 youngest. Same thing can be said for objects in real life that are not rocks. For example, this stack of pancakes. If you took the pancake straight off the griddle and put it on a plate, the oldest pancake should be on the bottom, and the youngest pancake should be on the top. This was the last one made. This was the first one made. First rock made, last rock made. Same thing for Cheerios. Like I said earlier, the oldest or the first stacked Cheerio should be on the bottom. The last stacked Cheerio should be on the top. In a layer of rocks, where the rocks are labeled like A, B, C, and D here, A would be the oldest layer, D would be the youngest, assuming that something hasn't gone through and moved these around, which is certainly possible. Now, let's look at the principle of original horizontality. Now, when we talk about sedimentary rocks are almost always deposited in nice, flat, horizontal layers. Why? Because, well, gravity. Gravity likes to push things down as far as they'll go. So, for example, this dry lake bed over here on the left, all the rocks from all the mountains and everything lands into this nice, flat area and spreads out. Because gravity wants to bring it down, but once it hits this flat area, it really has nowhere else to go, so it just kind of spreads out a little bit. For this sequence right here, it fills in this basin, so they're nice and flat, nice and flat, nice and flat. Now, it doesn't mean every rock is going to be flat. That's mostly sedimentary rocks. Some igneous rocks will also form somewhat flat, like if you have a nice basalt. Other igneous rocks may form peaks, like mountains. So it just depends, but mostly for sedimentary rocks, they will almost always be formed horizontally, flat. Which means if they're not flat, something went wrong. Now, for relative dating, when we're talking about relative dating tells us the order of events. What happened first, what happened second, what happened third, what happened fourth. It does not give us a number for how old a rock is. That's absolute dating. That's radiometric dating. That will tell us the exact age of a rock, but relative dating will not. So this rock could be 1 billion years old. It could be 1 million year old. We don't know. All we know is that this rock right here is older and this rock right here is younger. A is older, D is younger. That's all we know. Now, there could be ways to actually figure out the age of these rocks. Like I said, radiometric dating. Maybe you find a fossil in here that contains carbon-14, and that fossil we date it to be, 15,000 years old for this layer right here. Well, then we know that these rocks up here are younger than 15,000 years, and these rocks down here are older than 15,000 years. That's all we know. Maybe you find some sediment from the KT boundary or the big asteroid that killed the dinosaurs. Maybe you find it in this layer right here. Great. That tells you these rocks between here and here are somewhere between 65 million and 15,000 years. And these rocks down here are older than 65 million years old. But with relative dating, all we know is older or younger, not the exact age. We need something else to tell us the age. Now, so basically an unconformity is anything that causes layers of rocks to become missing, usually due to erosion. And there's 3 types of unconformities we're going to talk about. The first one is angular unconformities. Now, as you know from the principle of original horizontality, rocks, or at least sedimentary rocks, do not like being put down at angles. They are deposited in nice, flat, horizontal layers. And if you look at A, B, C, D here, they are not horizontal. They are at an angle. Something happened to move these to an angle. And not only did they get moved to an angle, but look, above them, there's this little squiggly line, and then there is a horizontal layer on top of them. So something happened here that got rid of layer A, B, C, D on top, eroded them away, and then all of a sudden, layer E got placed on top. What usually happened to cause this is maybe something folded them up, maybe plate tectonics folded them up, or an igneous intrusion like a volcano came by and moved them up, and then they got exposed to the air, let me tell you, air erodes rocks. So maybe some air came through, eroded these, or a glacier eroded them, or something like that. And then they ended up back underwater. And when they ended up back underwater, layer E got placed on top. So that is certainly possible. Many different scenarios can happen to make an angular unconformity. But I will say on the top of angular unconformity, it's no longer angular, it's now horizontal on top. So a great way to locate an angular unconformity, you have angled rock, angled rock, angled rock, angled rock, and then all of a sudden, flat rock, angular. That's probably the easiest one to find when you're looking for it. Let's look at the next type, which is probably the hardest one to find, and that's a disconformity. And the reason a disconformity is so hard to locate is it looks like all the rocks are there and that nothing is missing, but there is something missing. There's an erosional layer, so a little squiggly line if you're looking at a drawing of it, and then there should be something missing. Now, the problem with real life rocks is real life rocks don't have letters sitting on them. They don't have A, B, C, D, E. So you can't just go up and say, oh, look at this, B is missing. There must be a disconformity here. No, it's a little bit harder than that. You actually have to either find an erosional surface, or maybe the rocks look a different color, like maybe A is red while C is white or something like that. It's not perfect, but it is one way to tell. Maybe you radioactive date the rocks and you find A is 1.4 billion years old while C is only 200 million years old. That's possible as well. So if you use radioactive dating to figure out, hey, there's a lot of dates or a lot of age missing between A and C, that might be another way to tell you have disconformity as well. And the whole reason a disconformity happens is maybe layer A and B were exposed to the air and they were eroded over a long period of time, eroded by wind, water, ice, sunlight, plants, all sorts of things. And then they got covered by water or something, and then C and D were placed down. That's usually what happens. This nonconformity, which are a lot easier to find than disconformities. So for a nonconformity, what do you have? You have sedimentary rock that is placed down horizontally, nice. And then all of a sudden, igneous or metamorphic rocks come up from underneath, and they either take away some of it or take away the bottom of it. And now you have sedimentary rocks, which shouldn't appear like they appear right here, right? A shouldn't appear over here and on the other side. B shouldn't be cut in half. Half would be over here, half would be over here. So with a nonconformity, you can think, okay, sediments were there first, and then the igneous rock came in and destroyed some of those sediments. So sedimentary rocks on top of igneous or metamorphic rocks. Now, sure, you could have a metamorphic rock that gets eroded and then sedimentary rocks come on top of it. That's certainly possible as well. So it doesn't have to be an igneous rock intrusion. It could be just erosion and then sedimentary rocks on top. That is possible as well. Now, nonconformities are usually pretty easy to spot because there's a huge difference between igneous rocks and sedimentary rocks. Mostly sedimentary rocks form in layers, while igneous and metamorphic rocks usually don't form in layers. And often they're different colors as well. Let's take a look. So here's the Grand Canyon. And if you look, sedimentary rocks, if you've ever been to the Grand Canyon, most of the upper layers are all sedimentary, nice layers. So layers of sedimentary rocks, layers of sedimentary rocks. These are still sedimentary rocks, even though they're a different color. They're still in layers. And all of a sudden we hit right here, and all of a sudden the layers stop. No more sedimentary rocks from this point down. It's all metamorphic and igneous rocks down here and over here on the left as well. So this is a nonconformity, and in this case, it's also a disconformity because 1 billion years of Earth's history is missing from right here to right here. It's gone. It's been eroded away. So you get sedimentary rocks on top of metamorphic rocks, but you also are missing rock layers. So you get both. For the law of cross-cutting, when something cuts something else, it must have happened after. So what do I mean by that? Well, let's say that layer D is a layer of sedimentary sandstone. Should be nice and flat, complete, nothing cutting into it. Well, something cut into it. Notice that layer X here is not horizontal. It cut into layer D. X might be an igneous intrusion. So if X came in and cut layer D, X must be younger than D, and D must be older than X. The thing doing the cutting must be older. And it should make sense if you've got a piece of paper and you can't cut nothing. You need something there in order to cut it. So you need paper in order to cut the paper. Doesn't work without something there to cut. Okay? So in this case, X cuts D, and then notice how X gets cut by Z. I'll give you a hint. Igneous intrusions, they don't form giant spikes above the Earth's surface. When igneous rocks hit the Earth's surface, they flatten out. So Z would never, ever, ever form by itself, not like this. So Z must have cut into other things. In this case, yes, Z cuts X and Z cuts D. Notice how the line of X gets cut and Z is a continuous line. That must mean Z is the youngest, X is second youngest, and D is the oldest. Now let's say we take this scenario and we cut all of these with some erosion. Notice these wavy lines up here. So erosion cuts X, Z, and D. That must mean that the erosion happened after all of those things. So the erosion must be the youngest thing in this scenario. All right, that's it for the law of cross-cutting, relative dating, principle of superposition, and law of horizontality. Let's go ahead and try some practice problems now. So take a look at this.